The different types of sequences explained. In this section, we will briefly explain some types of sequences. We use the so-called term-to-term rules to get from one term of a sequence to another. 1. Arithmetic sequences. An arithmetic sequence, otherwise known as arithmetic progression, is a type of number sequence where the difference between two consecutive terms is always the same. Arithmetic sequences are also known as linear sequences. For example, we have the following shown on screen. Is an arithmetic sequence, as x1 equals 1, x2 equals 4, x3 equals 7, x4 equals 10, x5 equals 13, etc. So the difference between two consecutive terms is always constant, x, n minus x, n minus 1 is equal to 3. Hence, the pattern of this sequence is add by 3. If the difference between two consecutive terms in an arithmetic sequence is positive, the terms are increasing, otherwise, they are decreasing. For example, 19, 15, 11, where n minus 1 equals minus 4. The pattern of this sequence is subtract by 4. The difference between two consecutive terms in an arithmetic sequence is known as the common difference, d. In the first arithmetic sequence, we have d equals 3, while in the second arithmetic sequence d equals minus 4. 2. Geometric sequences. A geometric sequence, otherwise known as geometric progression, is a type of number sequence where the ratio between two consecutive terms is always the same. For example, we have the following shown on screen. Is a geometric sequence, as a1 is equal to 2, a2 is equal to 6, a3 is equal to 18, a4 is equal to 54, a5 is equal to 162, etc. So n over n minus 1 is equal to 3. The pattern of this sequence therefore is multiply by 3. Like in arithmetic sequences, if the ratio between two consecutive terms in a geometric sequence is positive, the terms are increasing, otherwise, they are decreasing. For example, 80, 40, 20, where n minus 1 is equal to 1 over 2. The pattern of this sequence, therefore, is divide by 2 or multiply by 1 over 2. The ratio between two consecutive terms in a geometric sequence is known as the common ratio, r. In the first geometric sequence, we have r equals 3, while in the second geometric sequence r equals 1 over 2. Example 1. Determine the type of sequence and the pattern in the number sequences. A, minus 3, minus 8, minus 13, minus 18. B, minus 4, minus 1, 2, 5, 8. C, 4, 2, 1, 1 over 2, 1 over 4. D, 4, 20, 100, 500. Then, find the next three terms in each sequence. Solution 1. A. This is an arithmetic sequence because the terms decrease by 5 when moving from left to right. The pattern, therefore, is subtract 5 from the previous term. The difference d between two consecutive terms is d equals minus 5. Moreover, this is an infinite sequence, as it has a beginning, minus 3, but no end. Following the given pattern, we find the next three terms. They are highlighted in yellow. We have the following shown on screen. B. This is an arithmetic sequence because the terms increase by 3 when moving from left to right. The pattern, therefore, is add 3 to the previous term. The difference d between two consecutive terms is d equals 3. Moreover, this is an infinite sequence, as it has a beginning, minus 4, but no end. Following the given pattern, we find the next three terms. They are highlighted in yellow. We have the following shown on screen. C. This is a geometric sequence because the terms increase by a factor of 5 when moving from left to right. The pattern, therefore, is multiply by 5 the previous term. The ratio r between two consecutive terms is r equals 5. Moreover, this is an infinite sequence, as it has a beginning, 4, but no end. Following the given pattern, we find the next three terms. They are highlighted in yellow. We have the following shown on screen. D. This is a geometric sequence because the terms halve when moving from left to right. The pattern, therefore, is divide by 2 the previous term. The ratio R between two consecutive terms is R equals 1/2. Moreover, this is an infinite sequence, as it has a beginning, 4, but no end. Following the given pattern, we find the next three terms. They are highlighted in yellow. We have the following shown on screen. Three. Fibonacci-type sequences. A Fibonacci-type sequence is a particular kind of number sequence where the next term is obtained by adding the previous two terms. In symbols, a Fibonacci sequence is expressed as x n equals x n minus 2 plus x n minus 1. For example, we have the following shown on screen. Is a Fibonacci-type sequence, as 0 plus 1 is equal to 1, 1 plus 1 is equal to 2, 1 plus 2 is equal to 3, 2 plus 3 is equal to 5, and so on. Example 2. Find the values of x, y, and z in the Fibonacci-type sequence. We have the following shown on screen. Solution 2. Since each term of the sequence is obtained by adding the previous two, we have the following shown on screen. Thus x equals 10. Yet, we have the following shown on screen. Thus, y equals 16. Moreover, we have the following shown on screen. Thus, z equals 42. 4. Quadratic sequences. Quadratic sequences are those sequences in which the difference between two consecutive terms changes by the same amount each time when moving from left to right. For example, we have the following shown on screen. Is a quadratic sequence, as the difference between two consecutive terms increases by 2 each time we move from left to right. We have the following shown on screen. Such sequences are called quadratic because they follow the pattern of quadratic polynomials functions, where the difference between two consecutive terms changes by the same value. For example, in the polynomial p, x equals x squared, the values of p1, p2, p3, and p4 are 1, 4, 9, and 16 respectively. You can see that the difference between two consecutive terms increases by 2 each time we shift to a higher value of the variable x. Example 3. For the sequence, we have the following shown on screen. This is a quadratic one. Calculate the next three terms of this sequence. Solution 3. This is a quadratic sequence, as the difference between two consecutive terms increases by 4 when moving from left to right. This means the sequence has the following pattern. We have the following shown on screen. Continuing this pattern with other three terms yields, we have the following shown on screen. Figure-like sequences. Sometimes, the patterns that certain sequences follow are similar to certain geometrical shapes. For example, the sequence, we have the following shown on screen. Looks like equilateral triangles formed by small balls that increase in size when moving from left to right, as shown in the figure. We have the following shown on screen. Another sequence that has a figure-like pattern, we have the following shown on screen. Which has a visual appearance as shown, we have the following shown on screen. And so on. 5. Shape sequences. Shape patterns can form sequences when they have some regularity. The most common shape sequences involve the enlargement or reduction of shape size according to a given rule. Look at the figure we have in the following shown on screen. We can identify two different patterns in this figure, the pattern of the black circles and that of the white circles. You can easily find that the pattern of black circles is add by 2 and that of white circles is add by 3. Therefore, we have two arithmetic sequences in the same figure. We have the following shown on screen. Moreover, we can obtain other sequences with specific parts of the figure. For example, with the bottom part of the shapes in the figure, we can form the numbers sequence 2, 4, 6, 8. With the upper part, we have the sequence 1, 2, 3, 4. The same for the left or right parts alone. Example 4. A. Write two sequences that you can identify in the figure. We have the following shown on screen. B. Find the number of white and gray squares in the seventh pattern. Solution 4. A. The shapes in the figure contain two colors, white and gray. The total number of squares for each of the colors forms sequences. Thus, total number of white squares sequence equals 6, 10, 14, 18. It is an arithmetic sequence where the common difference is d equals 4. Total number of gray squares sequence equals 0, 2, 6, 12. It is a quadratic sequence, as the difference between two consecutive terms increases by 2 when moving from left to right. B. Continuing the sequences for other three terms, to obtain the seventh terms of the sequences, yields total number of white squares sequence equals 6, 10, 14, 18, 22, 26, 30. Total number of gray squares sequence equals 0, 2, 6, 12, 20, 30, 42. Therefore, if we had a seventh pattern shown in the figure, it would contain 30 white and 42 gray squares. That is all for lesson 12.1.2. To continue this tutorial, please watch 12.1.3, Understanding Sequence Notation. Thank you for watching. Make sure to like and subscribe to keep up to date with new videos. For more information, calculators, and tutorials, please visit www.icalculator.info.